Hello, my name is Robert Smith, and I'm with New River Community College's Academic Assistants. And today we are looking at the standard enthalpy of formation and reaction. So what does that mean? Well, what we're basically looking at is edit. Hello, my name is Robert Smith, and I'm with New River Community College's Academic Assistants. And today we are looking at the standard enthalpy of formation and reaction. So what does that really mean? Well, what we're looking at is in a given reaction, what is the resulting heat? What is going to happen heat-wise? So you always want to think of enthalpy in terms of heat. And all you have to do is remember Hess's law, which simply states that the sum of the formation of the heat for the products minus the sum of the heat of formation for the reactants is equal to our overall heat of formation for the reaction, RXN. And that's all we're doing today. Now, the numbers that I'm going to be throwing out are taken from your book. Most, if not all, chemistry books will have a list of the standard heat of formation for all different types of molecules, specifically with the idea in mind that you're going to be using Hess's law or other thermochemical equations, and you'll need to be able to have access to them. What it won't do is give you the heat of formation for the entire reaction generally, and that's what we're trying to find out. We're trying to find out what is the heat of formation for this whole reaction, and we'll use the heat of formation for the individual components of the reaction to calculate that. So for this first one, we're going to call this number 1. It says your solid carbon plus oxygen gas is going to yield CO2. That's a reaction. Well, anytime you're looking at this, you're going to want to start with your products. Going to the table in the back of your book, you will find the standard heat of formation for CO2 is negative 393.5 kilojoules per mole. Now, if you're asking yourself, how am I supposed to know that? You will not be asked this on an exam unless they provide you with the heat of formation for the individual components. In other words, you don't have to memorize 393.5 kilojoules per mole for the formation of CO2. You just have to be able to look it up in the chart. And that is a technique that you will have to learn over time just through practice. Now, if you also look at that chart, you'll find that we're going to have to subtract the sum of the two heat of formations in the products. Well, we have carbon, we have oxygen, both of which, surprise, have 0 for its 0 kilojoules per mole for their heat of formation. So what does that mean overall? Well, that means that this reaction number 1, is going to result in a heat of reaction being negative 393.5 kilojoules per mole. It's putting out, releasing 393.5 kilojoules of energy for every mole involved in the reaction. For every mole in the reaction. Okay? So, equation number 2 is a little more complicated. We know that O2 is going to give us 0. So this is going to go to 0. We don't have to worry about it. This carbon monoxide, however, does have a heat of formation. So again, we're going to start off with negative 393.5 kilojoules per mole minus 0 kilojoules per mole. I'm writing this out explicitly for your benefit, plus the heat of formation of carbon monoxide, which is negative 110.5 kilojoules per mole. Well, if you look at this positive here, a negative times a positive is going to yield a negative. So this term becomes negative. A negative times a negative is going to be positive. So this overall term is going to be positive. So you have to do your PEMDAS. You have to do your parentheses and then work outward. So what this is saying is the heat of formation for this reaction is actually negative 283 kilojoules per mole, which is less than our previous one because you're factoring in the carbon monoxide's heat of formation. Let's do another one. It's very similar. Calculate the standard enthalpy of formation of carbon monoxide from its elements given in the following steps. So we're asked to do carbon monoxide. So when we're looking at these, we're going to look at this in a very simple way. Even though our reaction over here, the second reaction, these are the same as the ones we just did. Even though this one is proceeding forward in this fashion, what we're going to do instead is we're going to flip it so that it proceeds in the reverse. Whenever you flip a reaction, it's going to result in a difference of the signs. So the sign is going to flip as well for the overall reaction, which you can do out with Hess's law if you so choose. You can do the calculation and get the positive 283 kilojoules per mole instead of the negative 283 kilojoules per mole. But instead, let's just go ahead and do this out because it's the exact same numbers as before. We're going to say that step number 1 had a delta H of the reaction is equal to negative 393.5 kilojoules per mole. And because we're flipping this, so our new reaction for reaction 2 is actually going to be CO2 gas yields 1/2 O2 gas plus CO gas. And because we're flipping the reaction, we also flip the sign on the heat of formation. So this new heat of formation is going to be positive 283 kilojoules per mole. Now let's look at what the 2 steps in here are. Notice the first step does not include the formation of carbon monoxide, and we are asked to calculate the standard enthalpy of formation of carbon monoxide from its elements given the following steps. So we're going to call this half reactions. We're going to say that this is a step in the right direction. We're going to look at this as step number 1 and step number 2. So when we're adding this up, we're not just looking at the formation of carbon monoxide from CO2, we're looking at the formation of carbon monoxide from the combination, the synthesis of carbon solid and O2 gas from our step 1 equation. So coming back to it, all we have to do, as complicated as that sounds, all we have to do now is simply sum the two heat of reactions. So our true heat of reaction, delta HRXN, is going to be negative 393.5 kilojoules per mole plus 283 kilojoules per mole, considering this a step-based reaction. And in so doing, you will find that the heat of reaction of creating carbon monoxide is negative 110.5 kilojoules per mole. And you know what's significant about this number right here, is that if you go back to our first problem, what do you know? In the back chart of your book, it says that carbon monoxide is a heat of formation of negative 110.5. We found that exact same thing when we did our step reactions. So that shows the power of the Hess equation. So as long as you do this properly, you will always end up with the correct answer. Simply take your sum, which means you add up all your products, paying close attention to the signs, and then you're going to want to add up all your reactants, again, paying close attention to the signs. And then you're going to want to take all of those, the sum of all of those products, and subtract the sum of all the reactants. And you'll get your heat of